Hello, my name is Savannah Avery, and this is my Lab 3, which focuses on the magnetic field of a permanent dipole magnet, in this case, a bar magnet. In this lab, the purpose was to measure the distance dependence of magnetic field due to a bar magnet and compare the experimental values to the theoretical values calculated using the Biot-Savart law, as well as find the magnetic dipole of the magnet. This lab provides a model of magnetic field due to the magnetic dipole from a bar magnet at various points surrounding the magnet. It also uses VPython to compare the theoretical values of distance dependence as given by the Biot-Savart law to the experimental values I gathered and calculated. The results were that my experimental values of distance dependence n was negative 2.9243, while the theoretical value was negative 3. My predicted value for the magnetic field at a 45-degree angle was 1.05 e to the negative fourth in the x component and 3.1 e to the negative fourth in the y component, while the recorded value was actually 3.04 e to the negative third in the x component and 1.48 e to the negative third in the y component. My methods for this lab were that I used the iPhone app Teslameter as a magnetometer to measure magnetic field due to a permanent dipole moment. I calibrated this sensor along true magnetic north and then took various measurements of the x component of the on-axis magnetic field at distances starting where the x component was equal to 1,000 microteslas. I also measured the x and y components at the distance where, if using the on-axis magnetic field, the x component was 1,000 microteslas, but I rotated the magnet by 45 degrees. It's very important to note that in my measurements I made sure to compensate for the Earth's magnetic field. The most important law of physics dealt with in this experiment is the Biot-Savart law, which states that the magnitude of magnetic field on axis is equal to mu naught over 4 pi multiplied by 2 mu, again multiplied by 1 over r to the third, where mu is the magnetic dipole. We can manipulate this equation to solve for mu. There is also the known relationship between the magnitude of magnetic field of a bar magnet, which is equal to k multiplied by the distance to the n power, where k is equal to mu naught over 4 pi multiplied by 2 mu, and n is the distance dependence for the equation. We can manipulate this and take the natural log of this magnitude of b, which is equal to the natural log of k plus the distance dependence times the natural log of r. Here we have the experimental values collected and the graphical model of the natural log equation. As you can see, we have the natural log of magnetic field graphed against the natural log of distance. This gives us a linear model as well as the linear equation y is equal to the distance dependence times x minus the natural log of k. Using this value for the natural log of k and the previously known relationship that k is equal to mu naught over 4 pi multiplied by 2 mu, I was able to compute mu as 1.53 a meter squared. I then used this computed value of mu to create this computational model. I first wrote a function for the magnetic field of permanent dipole moment, which included mu. I applied this function to the magnetic field of the parallel axis, perpendicular axis, and at a 45-degree angle. Finally, I created this computational model with arrows representing the magnetic field due to the bar magnet. As you can see, the orange arrows looking in the right direction are the on-axis magnetic field arrows, and the orange arrows pointing in the left direction are the perpendicular magnetic field arrows. The blue arrow represents the magnetic field at 45 degrees. I found that my distance dependence was equal to negative 2.9243. This gives a percent error of 2.58% between this value and the theoretical distance dependence of negative 3 given the Biot-Savart law, which is a very good percent error. I did, however, find that my magnitude of my experimental magnetic field at a 45-degree angle was 3.38 e to the negative third, while my predicted magnitude of my magnetic field at a 45-degree angle was 3.33 e to the negative fourth, which is different by a factor of 10 and shows there's obviously discrepancies in the experimental versus predicted magnetic. Some interesting conclusions were that if I hadn't oriented my experiment to compensate for magnetic field north, then my graph, I believe, would look the same as the data is relative between the natural log of magnetic field versus the natural log of distance. However, the differences would be in the values, and therefore the differences between the theoretical and experimental data would be rather large. I also would have expected the measurements for the magnitude of magnetic field to double or close to double if I stuck two identical magnets together. However, the magnetic field does not change when the identical magnet is added. Thank you so much for listening to my presentation.